You want to say
What's that? Oh, right. So let's turn in the homework. Thank you. Let's leave Wednesday's date on it. Okay? So keep it as Wednesday's date on there. Okay, as you're putting your heading on, turning it in, I've got an image up here, which should look very, very, very familiar. So I want you just to talk for a minute and identify everything you can about this, make sense of everything, which there should be no mysteries here. Everything is reviewed. So just have a conversation and talk about every aspect of this that you can. So talk about every aspect of this picture as you can for a minute. Go.
I think that's showing accumulation. For established dots represents the accumulation from one of those intervals. I think I'm not sure.
okay, so
All the homework turned in?
Accumulated. Like first it's a lot, and then it's a little less, and it's less, and it goes less, and it starts increasing. Yeah.
Okay, so and then what's the meaning of this point, this black point? What's the meaning of this point? And then what does all that stuff have to do with it? Okay, so what's the meaning of that black point, and what does all that stuff below it have to do with it? Keep going.
Yeah, black.
So is that already going to be accumulation? Yeah. I was about to say that, so it's all sort of blue points, just because that'll be that total accumulation.
Oh, yeah, to that. Yeah.
Okay. Let's see.
Yeah, the change in the last one is a lot smaller than the change in the first one.
David, what did you talk about? Anything you get to choose. You're first, so.
The left hand graph was our step function of the different rates across different intervals.
Okay, so what is the step function specifically?
Mid step function.
Okay. Is there only one function graphed here? There's really two graphs here, right? Two functions. So I guess it's obvious, but which one are you looking at when you say it's the mid step function?
The rate of change.
Do you see that there's two functions graphed here? There's two different functions graphed here. You should see that. You should see that there are two functions graphed here, not just one. Kaylin, do you see that? So he's talking about the mid step function. Which one is the mid step function?
You mean which one?
Yeah, go ahead, James.
There's three functions. There's the
No,
rate
over here on the
function.
left.
Yeah, there's the rate function, which is red. There's the step function, which is the blue lines, and then there's a y equals 4.1 and less than greater than as well. There's three functions.
So you're looking at this?
I'm looking at the red line, which is the rate function.
Right.
The step, which is the step of r of x, and then the third function is y equals 4.2, 4.1, whatever that is. There's three functions over there.
You're looking at this right here?
Yeah.
That's not a function because it's a vertical line. So But yeah, this is a different element of the graph. Right, but he's right. The red function is our exact rate. The red is the exact rate. The blue function is our mid-step function. Okay, what else yeah? I'm recording, yes. Thank you. All right, what else, so we got the rate down, and then also we're kind of pinpointing 4.1. Seems like x equals 4.1 is what we're highlighting. Okay, what about over here? Sean, tell me anything that you made sense of over here. Anything at all?
I'm trying to here. Would those be like with the step points for the weather tree?
What are you looking at?
Well, the graph on the right, where there's all those dots, is that where you'd otherwise have your delta x's?
Are you looking at this right here?
Yeah.
Okay.
Would those be the y values that correlate with the delta x's?
The y values that correlate with the delta x's. What do you think?
It's just
Janae, he's asking about these blue dots.
I was trying to think the same thing for the step for shortening.
Nice and loud.
I was kind of thinking along the same lines that the dots were representing the step, but representing them differently.
Okay. What do the dots represent? Do they represent the steps, like the values of the rate? Is that what those mean? Steve?
It represents, well, the first dot represents the accumulation during the up to the first interval.
Okay.
So they're shrinking because the rate is going down.
Right. Okay.
So like the distance between the dot and the x-axis would be the accumulation.
So you're saying these are bits of accumulation, little changes in y, right? Yeah. So it's not the rate, but it's the rate times delta x each time, which gives a little bit of accumulation. And then the meaning of this point. Meaning of this point. Jonathan.
Just last one.
Uh-huh. The black point right there at the top on the red graph.
Well, that's the total amount of accumulation at that point.
Okay. What about that point is the total amount of accumulation?
Y.
Right, so there's two coordinates to that, right? 4.1, and then maybe something around, who knows? 4.5? I'm just guessing there, this is about there. Maybe 4.4, too high. Okay, so he's saying the y value is the total accumulation when x reaches 4.1. Starting at where? Yeah, we're accumulating, so our a value is 1. We're accumulating up to 4.1. And that y value of that point then is the total accumulation as x changed from 1 to 4.1. Okay? And so then how does that total accumulation relate to this blue line again? Austin, how does that total accumulation relate to that blue line?
It shows the bits of accumulation based on the step function.
Yeah, so we add up those bits. Okay? So we add up those spaces in the blue segments are the bits totaling up by the steps to this 4.5. Okay, so we said, so from rate 1, we get a little bit of accumulation, R1 delta x, right? And from rate 2, we get another little bit of accumulation that's less than before. Okay, so this is our understanding of it up to this point. So the accumulation then can be a wide variety of things, right? So what are some examples of quantities that we could be accumulating? Just shout them out. Anything. Height. Distance. Temperature. Temperature. Weight. Interest. Someone said money. How about population? Work, right? Physics. We could spend 10 minutes listing things. Okay? So this whole thing that we built up really applies to any quantity that can be changing, right? That can be changing relative to another quantity. And we have its rate curve, and so then we can calculate the accumulation of that quantity for which we have the rate, and it could be all these different things: height, distance, temperature, weight, interest, population, work, profit, cost, right? Anything. So here's an alternate understanding of integrals, which is actually the primary understanding for more of a traditional sense. Okay. This is how the kind of traditional calculus has really focused in on this understanding of integrals. So you notice that this first rate can be represented by this distance right here. Do you see that? From here to here. And then delta x can be represented by this distance here. And we're multiplying R1, this represented by that height, times delta x represented by this width. Do you see that? So what might this alternate understanding be? Yeah.
Area.
Yeah, so that R1 delta x could be seen as an area of this rectangle formed by the top by our step, and whose width is delta x, and the height of it is the rate. You see that? So then the next step would give us the area of that next rectangle, or the next. So do you see that? The rate is like the height of the rectangle, delta x is like the width of the rectangle, and since we're multiplying them together, it's like the rectangular area rectangle formula. Okay? That integration is remotely related to areas of rectangles is entirely an artifact of the fact that we're graphing in rectangular coordinates. It's kind of like a coincidence, right? It's kind of like a coincidence because our delta x is horizontal and because the way we graph, the rate is vertical. It just coincidentally or incidentally creates the formula for the area of a rectangle. It's not a deep mathematical principle. It's just an artifact. It's just kind of this thing that happens because of the way that we graph. But most of the calculus world sees integration this way. Okay? So we want to make sure that when you go on to further calculus courses and you're rubbing shoulders with other students and reading textbooks, you have. I'm going to give you a context here to relate to. So this thing that's the area of a rectangle, what is it for us? What is that quantity that we're showing here as an area of a rectangle? What does that quantity mean? What's that? A little bit of accumulation, the change in y. So whenever you see this thing about adding rectangles together, say, oh, I know what that really is. See? I know what that really is. What that really is the rate times the change in x, which gives me a little bit of accumulation of something like this: height, distance, temperature, weight, interest, population, work. So integration truly is not about area, but over time in calculus education, it's become about area. Okay? I'm telling you the truth here. I'm telling you the truth. So, and as you continue taking calculus courses, like I said, looking at textbooks, talking to your friends in other calc courses, the focus is going to be this area thing. But we know better. We know better. Each rectangle is a bit of accumulation, or is another way of representing a bit of accumulation of some real-world quantity that's changing. Okay, so I hope you got that, and you're not too focused on getting your homework. Okay. So what happens if we make delta x smaller? So here's a smaller delta x, right? So we know that as smaller bits and a more accurate pretend rate function and then smaller bits added, lots more smaller bits added together. So what does it mean for rectangles?
It's smaller.
Skinnier, right? Skinnier, and the tops of those rectangles are matching the curve better, right? Skinnier rectangles, the tops of this matching the curve better. Until they get this idea of dx, right? So the idea of dx meaning as small as you can imagine, atomically small. And so what is this value of the integral then approaching? So we know the value of the integral. So the value of the integral from 1 to x of rt dt. What does that mean for us?
That means all of the accumulation from the first interval to whatever interval x is.
Right, total accumulation of our quantity, whatever y is in this graph, from 1 to the current value of x. In this other understanding of integrals, what does the meaning of that? What are they saying the meaning of that is?
The area under the curve from 1 to x.
Right, so it's this blue shaded area. As those rectangles get super skinny, then what happens is the sum of those rectangles gets very, very close or indistinguishable from the area. Okay, so probably what we should talk about is then what happens if our rate curve goes negative? All right, and we're going to say we're going to go from 0 to 10 here. This is our rate. Okay, so what's going to happen? So we're talking now about the integral from 0 to 10 rt dt. What does it mean for us?
The accumulation from 0 to 10 of our x.
Right, so it's the total accumulation from 0 to 10. And let's kind of break that down. What happened along the way as we accumulate from 0 to 10 with a rate like that? What happens along the way, Christian?
The rate became like a negative rate, so like at some point the quantity was decreasing.
Good. So at first the quantity is increasing, and then our quantity through here decreases, and then increases up again. So that's all taken care of in this, right? That's all taken care of this, and then we get the total result, the change from 0 to 10. The total change from 0 to 10, taking into account that it's actually that quantity is decreasing through here when the rate is negative. So then what's the equivalent kind of area? What will this find equivalently as area? What will it be? So if you want to interpret this with this area construct,
So
what will this give us relative to areas or area? Yeah.
is that like, so from 0 to 2 or whatever, area is positive?
Positive contribution, right?
Yeah, and then from 2 to 8 or whatever, it's negative and then positive again?
Right, so is it going to find you the total area of those three pieces?
It will be like 0.
Will it add up this area plus this area plus this area?
That area.
No, right? We know what this does. When the rate is negative, what happens to the accumulation? Does it go up or down?
Down.
It goes down. So it's like going to add this area, and then it's going to subtract the value of this area, and then add this one in. Okay, see? That's what you're
Is
saying.
that like,
What's that?
I don't know, was this like in high school calculus, you made it for like plus signs and then minus signs on like certain intervals of the graph and stuff?
Right, but so based on accumulation, that's easy to see, right? Oh, the rate is positive, so it'll be going up, and now my accumulation is going down, and now my accumulation is going up. So that's why if you interpret it interpret it with areas, you have to find this area and subtract it.
So how do they get around that when if you look at an integral like that?
You know what it means.
I mean, like if we didn't know its accumulation, how would you get around that?
Get around it.
Because you're going to be subtracting the negative, or you're going to be subtracting the negative from your positive.
Right.
So what would you do if you didn't know, it's accumulation, you know, the rate's positive, and then negative and positive.
I'm not understanding your question. You're saying you don't have the graph?
No, I mean like, so we know, because we learned it this other way, that the rate's positive and then it's negative and it's positive again, so it's tracking it. But if we just got taught the other way, like we did in high school,
Right.
what would you do? I don't remember.
You would have to understand what this calculates, okay? So you can still calculate this, and you're still going to get the exact same answer.
Oh.
But what you have to understand is, it's not adding up these areas. It's taking these two added and subtracting this one.
Oh.
That's what that's doing. Is that better?
Yeah.
Yeah, so it's just a matter of knowing what it's doing.
Okay.
Okay, so you'll have, my math lab is practice with what's called Riemann sums, okay? So we've been summing r times delta x, okay? And what that's called a Riemann sum. And so when they refer to Riemann sums, they're talking about adding up the areas of the rectangles. For us, it means adding up bits of accumulation. Okay, so your practice problems will be now in the context of adding up rectangles. Okay, and that's what they're calling Riemann sums. R-I-E-M-A-N-N. So area of rectangle 1 plus area of rectangle 2. So
So my math lab is going to be asking us like in the context of.
it's going to be saying, it's going to show you pictures of rectangles and say find the total area, find the Riemann sum, and by that they mean you're going to look at that and say I'm going to add up the areas of these rectangles.
But we know that it just means I'm the total accumulation.
The area of a rectangle is r delta x,
Okay.
which is a delta y, which is a bit of accumulation of whatever quantity this is. Okay. Questions on that? So yeah, so Riemann sum. Area of rectangle 1 plus area of rectangle 2 plus area of rectangle 3. And that's just R1 delta x plus R2 delta x. Okay? And just like we had left, mid, and right, so with rectangles it's the same thing. How are you determining the height of your rectangle? Are you determining it with the left side of the interval? With the rate at the middle of the interval, or with the rate at the right end? Same, everything's analogous, everything's the same. So you shouldn't be difficulty with this, as long as all you need to see is that connection between r delta x and the area, how that in rectangular coordinates, that turns out to be the area of a rectangle. Any questions? Okay. Got to pull up this one. I don't know if I'll be able to find it fast. Bear with me here. Forgot to pull something up. No, that's not what I want. Darn it. Back one more time. See if it's here. Okay, yes, found it. Thank you for your patience. All right, so this is what we've been doing, right? Accumulation from rates. We started with a rate function, and we built an accumulation function from it. Okay, so now, and so that was the idea from the very first day. You know how fast something is changing, you want to know how much of it you have. And then we said the other side of calculus was, you know how much you have, you want to know how fast it's changing. Okay, so that's what we're going to do now. So now, given how much you have, accumulation, what's the rate? Okay? So let's just kind of overview. What did we do? We started with exact rate of change, and we went to Step function, approximate rate of change. From there, approximate accumulation.
Exactly.
Did you get it right on the test? Did you get it right on the test? Okay. So so we did all this. We put in all the long hours, right? We paid our dues, right? We paid our dues with all this stuff so that we could just say, if we have an exact rate, we know what the exact accumulation is. This, right? But we earn the right to say that. Go right from exact rate of change to exact accumulation with all this hard work we did to build up that accumulation function. Okay. So what now? Going the other way. So now we're going to talk about. Start with exact accumulation, build an approximate accumulation, from that an approximate rate of change, and then get an exact rate of change. This will be a much shorter journey because all these tools that we developed in the process we already have now at our disposal. Like for instance, left x. We don't have to build that again. We know what left x is, right? It took us a day or two to build that. And so all those tools that it took in our first endeavor, now we have to use as we're reversing the process. Okay, so that's just an intro. So there is still a couple things we need to do this that we haven't talked about yet. So the first one relates to how fast did you run?
It was 30 minutes.
How'd you answer that, Alexander?
Like 10 points, an average speed is 10.2 meters per second.
How'd you get that?
Just distance you ran divided by total, whatever how long it took you to run
Okay, so you took the distance you ran and you divided it by,
that. 9.58 goals.
and you said you got
10.4
10.4, how about one more decimal place?
meters per second.
No,
10.4,
4.
4? And I heard you say that was his average speed.
Yeah.
Okay. So did he run that fast or not? What do you think, Gilbert?
What was your question?
Did he run that fast? Is that how fast he ran?
I believe he ran a little bit faster at some time because he
Okay.
started at 0
Okay.
meters per second. So he had to get up to his top speed, and he was below 10.44 meters per second at some point, which means to average it out, he had to be above that at some point.
Okay, so he's saying that he ran slower than that. He also ran faster than that.
Yes.
Yeah.
But I thought you were going to calculate me his speed. Now you're saying you ran slower and you ran faster. Aaron?
It's just really hard to actually find the exact rate because, like what he said before, because he could be running faster, which increases his rate, which he could be slowing down, which decreases his rate. We cannot specifically get an exact rate. We really get an average so far.
Okay, so you're saying average. Christian?
I mean, I would just say, like, the only thing that I can tell you without reservation is that he ran, 100 meters per 9.58 seconds.
Okay.
So it's like the rate across the interval from 0 to 9.58, like we were doing step function.
Okay. So what are you imagining? You're imagining what? The step function.
His rate is whatever, it's a function, and then on the interval from 0 to 9.58, that's the rate. So whatever the step is,
What kind of rate?
it's constant rate.
He's saying that's a constant rate. Yeah, Steve?
Would that just be like the middle step and then calculated through the entire way he ran?
So make that into a step, like our step functions, for the entirely the same thing they're saying, for the entire 9.58 seconds. Okay? So, but was that his race? Does that represent his race? Zoe?
Wouldn't that be like the approximate rate of change?
Okay, approximate rate of change? Shayna?
Yeah, because wouldn't we have to know where he was at each point in
Okay,
time?
right.
For us to know the exact rate?
Okay?
Because then we could, if we break it into smaller intervals of seconds, then we could know how fast he was going at each second.
Okay, so you guys are all, these are all great comments. Okay, Usain ran with what? Changing speed. But when I asked you to calculate his speed, we ended up with what? What kind of speed did we end up with? A constant speed. So, and you said this is average. His average speed, how can you then describe what his average speed is? His average speed is? What is his average speed?
Average speed is the speed required to cover the same distance as the changing rate.
Okay. He said required to cover the same distance. Ross, what do you think? What is average speed? We just got one number, right? What is that? What is that one number? It's this average speed. What does that mean? The question is, he ran with a changing speed. We calculated, we took his distance and his time, we just got one number, although he ran with a changing speed. So how can we make sense of that number relative to his race?
It's
What's that? 1y value? I'm not giving up on you. I don't want to take all that out. But so anyway, I recreated his race. So this is a recreation of his race, okay? So Marco, you were going to chime in.
I was just gonna say distance over time.
Distance over time. But the question, yeah, so that was his distance and his time. We got this constant, we got this rate that's not his race, because his race was a changing speed. So what does that number have to do with his race?
Change of x over change of y.
Change in x over change in y? Yeah, go ahead.
If you added up every single speed and then divided by the total number of speeds, that would be the average speed there.
Okay. We want to think of it in a different way than that. So how can we think of it in a different way than that, Zoe?
total change in y over the total.
Okay. Total change in y with total change in x. Give us this one number. We just got to, all you guys, you had all the bits and pieces. We just got to put it all together now. You guys had said it. So let me give you some help. Here we go. Ready? Watch. Here we go. There she is. Okay, watch it again. Here we go. 2, 1, go. Okay, talk about what you think you're seeing here. I'm getting at the point. What does this number mean? What does this number mean? Go. Okay, so the question we're asking is, what does the 10.44 have to do with his race? It came from his race, but you told me that wasn't his race. So what does the 10.44 have to do with his race? Peter, any idea?
If you were to start at 10.44 seconds and not change the speed when you accelerate, then you would cover still at the same time as you actually ran.
So if he ran at what? That's right.
10.44 meters per second for the entire 100 meters, he would still finish it in the same amount of time.
So run the same distance in the same time. That's what he said. So now we just want to generalize all average speed then. So not necessarily 10.44. So what is that 10.44?
The rate you need to do that.
We're getting there. Constant, right? Yeah, everything you said was right. So, okay. Well, and we're talking about speed here, so we'll leave it right at speed. Yeah. Right. This is what average speed is. It's a constant speed to cover the same distance in the same amount of time. So it's like you have to have another runner. You have to have another runner to compare it to who's going at a constant speed, covering the same distance at the same time. That's what that number, that average speed means. So it's a different, so adding up all the speeds, it's not like averaging your test scores, right? It's not an arithmetic mean. It's a constant speed that gives the equivalent distance in the same amount of time. Okay, so now I have his graph of his time and distance. There it is. So there's the graph of his time and distance. So if I made a graph of Emma's race representing his average speed, what would it look like? Talk to the person next to you. So if I'm going to graph Emma's race. Graph Emma's race. So Emma, that race represents, so this constant speed of, what was it, 10.44? Represents the what?
Average.
The average, yeah, go ahead.
Average.
Average speed of?
Usain.
Right. Of?
His actual.
Usain's, right. Actual race. Okay, so the big point is that average speed is a constant speed. Average speed is a constant speed. So if we take that, any questions? Does this make sense? And so, and basically, they went the same distance, so they had the same distance traveled at the starting point, 0. in the same amount of time. So at 9.58 seconds, they both covered 100 meters. Okay, so let's take this out of the context of speed and just any quantity. So suppose I have I have a vase like this, or like a bar glass. Okay, and say that it's filled with water. Okay, and because most of you are freshmen. Okay, and say when it's filled up to a height of, I don't know, 16 centimeters. Is that too much? Yeah, probably 13 centimeters. That's, I don't know, 15 ounces. Now let's do something different. $48 milliliters. I'm just guessing here. I have no idea if that's accurate. Okay, so when it's filled up to 13 centimeters tall, there's 48 milliliters in it. And so this is the number of milliliters of water. And this is the height of the water. So I want you to ignore the scale, all right? So ignore the scale. These numbers aren't right, but just imagine a graph where we're going to let the number of milliliters increase and the height's going to increase. So first question is, can you get a rough sketch of what that graph will look like as you start from 0 milliliters and start filling it up? Can you figure out what the height in that glass will be? And then, so at 13, so here's, say this is 13, this is 48. What's that? Yeah, thank you, sorry. 48 milliliters, 13 centimeters. Okay, and so can you sketch the graph of this as the number of milliliters increases, how the height increases with it, and then answer the question, what is the average rate of change and what would it mean? So what's the meaning of and value of the average rate of change? Go.
If it's constant,
Yeah, the average, yeah,
it would be 30 milliliter. It's just like talking about height increase per time.
yeah, but since getting bigger,
But it's not just because you got to change the price like that. It's going to put the at the beginning and it's going to have
Okay, graph first. Draw it with your finger. I think most of you got it. It's going to, the height's going to change more quickly at first, right? For less, when there's less water in there, the height's changing more quickly, and then it's going to change more slowly like this. Okay? What is the average rate of change in this situation? Anyone calculate it? Is it 48 divided by 13 or 13 divided by 48?
13 divided by 48.
13 divided by 48. And what do you get?
0.271.
0.271. What are the units on it?
Centimeters per milliliter.
Centimeters per milliliter. Okay, what's the meaning of that number? What's the meaning of that number? 0.271 centimeters per milliliter. So just as an extension of the speed situation, but now it's not really speed anymore because it's two different quantities other than time. All right, Nicholas.
Means for every milliliter of liquid you add to the glass, the height will increase by 0.27 centimeters.
All right, what do you think? For every milliliter that you add, the height's going to go up 0.271 in that class.
Well, for a constant.
For a constant rate.
Yeah.
What do you think? What is the meaning of 0.271?
Like that means that yeah, it's like the average